Transition metal chalcogenides are materials which are family of materials with properties that assist in many applications, including photodetector, optoelectronics, etc. For here, I am predicting properties of transition metal chalcogenides for photocatalytic water sweating. This is a schematic diagram of photocatalytic water sweating. So there are specific conditions to be met so that the TMC can be used for water splitting. From our predictions, by applying the condition, we can narrow down the list of material for prediction of materials for photocatalytic water splitting. So in this tutorial, I am showing how to do that. This is VS Code. I am showing this time in my local system. As I said, I am using this in my local system. This is Visual Studio Code. You can install from the official website. So these are the Python code I have made for the to generate the material list of transition metal chalcogenides. So we already have how to generate. We already know how to generate composition-based feature vector. If you have the formula for all the transition metal chalcogenides, we can make the feature vectors. Then we can make the predictions. Using that predictions, we can make the list of material for water splitting application. So this is the block of code to generate TMC with the formula M2X, where X can be any chalcogenides. So I have created a array of list for all the transition metals in three in different group, like group 4 to group 13 with a 3 group, and these are the arrays I have created for groups having the valency 1 and 2, group having the valency 3, and using the bigger list I can make the material compositions. These are the chalcogenides with the valency plus 2. These are the valency minus 2, means minus 1 and minus 2, minus 3, minus 4 up to minus 7. The gold and copper is added to this list because they have the valency 4 and 5 extra. So if you run the code M2, this block of code, you will be able to generate material of the formula M2X. To run the code, you can type first you need to change the directory into the test folder, cd test. Then we will run the Python code. Python, the file name m2x.py. So these are all the list. To put the output into a CSV file like this, you can use the following command, like put the angle arrow and put it into, for example, m.csv. So the output will be now in m.csv. This is a CSV file. So I have already done for all these M2X, M2X2, M2X4, like all these material list, and using this Jupyter notebook. I combine all these data frame into one big CSV file. To run the this Python files in the VS Code, we need to have to install Anaconda. After installing Anaconda, you can run Jupyter Notebook directly in the terminal by typing Jupyter, or you can run it in the VS Code by connecting the kernel, which you have created the project environment I have created. You may need to refer the Anaconda tutorials to know more about Anaconda. So you will create a big list of MNXN, this one, CSV file with all the transition metal chalcogenides. Like previous steps, using the packages that we already know, we will make predictions using the formulas that we just created. You may need to install composition based feature vector. If you have not already, then we will import the packages pandas, standard scalar, generate features. We don't need these two. We are not mounting Google Drive because I'm using it on my local computer. I'm loading the saved machine learning model. In this case, I'm predicting 2D plasma frequency. The best model was extractive regressor and featureization scheme was Olining. After hyperparameter optimization, the model is saved on the folder save model. Using this line, we will load the model into the model variable. So we don't need to train again, as I already showed in the last video. So then we will load the M2XN CSV file, which contain all the material list. We are going to predict all the TransitionMetal chalcogenide list. Then we will rename the headers, put the target value 0 for now. Then we can do the composition with feature vector. Featureization scheme is Olining. As you see here, we have used Olining. So after featureization, then we will predict the y values, which is output using model.predict command, model.predict functions, and we will sort. We will just output the data frame, which have 4496 rows and 2 columns, and we will rename it into formula and target to 2D plasma frequency X. Then we will add the prediction into M2 MNXN CSV, which we will populate first time with the 2D plasma frequency X. For next prediction, we will populate the 2D plasma frequency Y data. So after many runs, this will how it will look like. To contain all the 21 predictions that we are making. And we will save the data frame into this file using this command. After making the CSV file, we can use this Python file, Jupyter Notebook, to calculate the necessary conditions for the photocatalytic water splitting, like band alignment, values, etc. Then that can be added into the CSV file. You can save that into this CSV file here, MNXN_cal. Then we can apply the condition, we can select the material that obeying the conditions for photocatalytic water splitting by opening this Python file, Jupyter notebook file. Actually, you need to connect to the kernel project, which you need to make using Anaconda, and install the necessary packages beforehand. So we will read the mnxn_csv file in the df data frame. That data frame is here with the 4,496 rows and 24 columns now. These last columns are calculated values, like VBM_HSC minus evac, which is vacuum level, and CBM_HS minus evac for the prediction for the selection of material for thermodynamic water splitting, photocatalytic water splitting. So we will apply the necessary conditions using these lines for water splitting. The band alignment should be less than minus 4.059. The valence band maximum value should be less than 0.5 minus 0.62, and conduction band minimum value should be greater than minus 4.42. When we are choosing material with the excited bending energy less than 1 and thermodynamic mixed electricity level greater than 2, the band gap should be greater than 1.6. Band gap should be between 1.6 and 2.6. For the prediction of other property, you may choose the appropriate materials properties for your application. After applying this condition, the df condition file data frame contain 240 rows between 240 materials obeying the conditions. We will save these material condition into this df_condition CSV, and we will save. These are the materials that obeying the conditions for photocatalytic water splitting. So these are the materials that obeying the conditions. As you can see, the prediction using machine learning can be done very fast with your own laptop. Unlike traditional method, simulation method, you need a powerful computer. You may check the accuracy of your prediction using DFT or another simulation based methods. The machine learning will accelerate the development of new novel materials.